Hello everyone, my name is Kelson Hughes. I'm here with Team 02, and we are presenting our product, Sunseekers, which we designed for the VT student market. We are pursuing an opportunity we identified about improving the sleep quality of Virginia Tech students. Our product aims to retrofit a student's set of blinds in order so that blinds can be automatically opened and closed at a desired time, replacing the functionality of an alarm clock and improving the quality of sleep. We identified a customer profile, which is a Virginia Tech student looking to improve their quality of sleep and feel better when they wake up in the mornings. Our use case is, as previously mentioned, we'll be putting the blind retrofitting device in the student's room, and it will go off either before or at the time of their alarm clock, allowing them to experience some natural sunlight early on in the morning and smooth in their transition from being asleep to being awake. We developed a set of 5 customer needs based on their importance to functionality. The first need is they control the amount of light entering the room. The second need, the blind angle is adjustable. Thirdly, the blinds can open and close automatically. This is our unique need and what makes our products sellable. Fourthly, the blinds have a simple and ergonomic mechanism of opening and closing. And finally, the blinds block a greater amount of light than current products on the market. Moving on, we did a functional decomposition of the problem in order to present the 6 key functions of our product that needs to exist in the final solution. First off, the product must store and accept energy, convert that energy to mechanical output, connect to an existing blind component, therefore retrofitting it, apply mechanical output which rotates the blind twist rod and opens and closes the blind, and also it must take the user input which defines the time which the blinds must open, and then cue the device actuation. Nextly, we did a large concept generation process, very broad, and then used selection and screening to first narrow down from a large set of 16 possible concepts into just 6 and 8, and then chose our top 3 concepts using a scoring system. Our final concept is a solution of a wall-mounted approach powered by a 9-volt battery using a slot which holds the twist rod for easy disconnect and reconnect, and it uses a servo motor in order to turn the blind. We followed the design process to create a great design for the VT student market to improve sleep. Firstly, doing intellectual property research to ensure that our design was both proprietary, acceptable, and not stealing from somebody else's design. Then we did FEMA analysis in order to identify potential failure points and improve our design to make it less prone to failure. Nextly, we did design for manufacturing, design for assembly, and established a bill of materials in order to investigate the cost and time requirements for mass producing our design. And then finally, we designed and built a final prototype, and I'll show those steps to you in greater detail now. Firstly, patent research confirmed that our design was novel and plausible, which are the requirements for making a new design on the market that does not infringe upon other established patents and would allow us to create our own patent for our design. Nextly, we did FEMA exercises to identify key failure points that we could improve upon. The first key failure point was that our wall mount would be at an angle from the twist rod due to the twist rod being very close to the wall, but the device itself having to stick off a few inches of the wall. Our solution to this was creating a headlamp-style twist system which allows the mounting box to be mounted at an angle to the wall so that the twist rod can better connect without putting a shear stress or a bending moment on the twist rod. Secondly, we established a better option for connecting the twist rod to the mounting box, which would result in less slippage and improve the sureness of our design to hold the twist rod and have enough friction to prevent the twist rod from slipping when the torque was applied. Next, moving on, we used the Boothroyd-Dewhurst tables for estimating a DFA cost and time estimations. So we calculated the amount of time that it would take for each motion of assembling our product. The time to assemble the first unit was calculated at 89.83 seconds using the Boothroyd-Dewhurst tables. Next, we chose a high learning slope curve parameter of 0.98, which was chosen because the manufacture or the assembly steps of our design are quite simple, and there would likely be little to no improvement over time for a worker because there's no skill ceiling for these types of operations. However, there's always some learning that will happen, so that's why our learning curve parameter was not 1. And then our break-even analysis decided that our break-even number of units to sell was 286, and so the average time per unit in assembly for the first 286 units was 78.43 seconds. We decided on an average pay rate of $15 per hour because it is very low skill work, so close to the minimum wage would be acceptable. And this gives us an average cost per unit for assembly of just 33 cents per unit. Nextly, we used Protolab Inc.'s quotes for DFM cost and time estimations. This is one example of a Protolab's quote for 3D printing, and we summed all of these quotes for our 4 manufactured parts in order to establish our bills of materials. Now here's a summary of our various bills of materials which our team established. We did these based on 3 different types of manufacturing types that we had options to use. The first one is local 3D printing, which we used for our original first prototype. This just means that somebody's home 3D printer was used to print the parts which we needed, and the total cost, including the manufactured and bought parts, was about $70. Next off, we used the 4 Protolab quotes for 3D printing mass manufacturing and established a total cost of $770, which is extremely high and also probably not plausible because the cost of 3D printing over a large amount of units would not decrease very much than just 1 unit because the process does not improve in efficiency over time. Finally, Protolabs also gave us quotes for injection molding, and the initial cost for the first unit is extremely high at over $25,000. However, for injection molding, that cost is mostly put into the extremely high front-loading cost of creating injection molds, and it is much likelier that the cost would exponentially drop over time as the molds can be used over and over and over again. And so, even though our break-even analysis would likely skyrocket into the thousands or tens of thousands of units to break even, after that number was achieved, we would experience profit much quicker than the other 2 methods. Nextly, we finalized our CAD model in order to visualize and confirm our prototype, and we used these CAD pieces in order to create our 3D prints of the model. This is our final prototype. It effectively demonstrates how the design fulfills all the intended design specifications. As you can see here, these are our 3D printed pieces. We have our 9-volt battery, Arduino board, breadboard, servo motor. Here's the twist clamp rod, and there is a blind twist rod inserted into it there, which demonstrates how it would be mounted in a real bedroom. In summary, Team 02 developed a strong product to meet the need of improved sleep in the VT student market. We established a set of customer needs and designed a prototype that proves the design is feasible, and we demonstrated this prototype in class. Secondly, we demonstrated the design fills the customer needs by achieving its intended purpose and meets all specifications. Finally, we decided that our design would be profitable based on our break-even analysis and our estimated costs of manufacturing and assembly. Students and other customers can effectively benefit from this design, and they will wake up more energized, and our product will be a great addition to the student market at Virginia Tech. Thank you.